So we could rewrite this as what?
Secant squared 2x times dx.
All right, secant squared 2x times dx, which is probably a little bit better, right? Because there is a rule for secant squared u and du, isn't there?
Yes.
Yeah. The problem though is we have secant squared 2x. So what do we need to do to deal with that 2x?
Substitute it for u.
All right, good. So we'll let u equal 2x. If u is 2x, then du should be what?
Two.
Yep, 2 dx, which means we'll need to put in a 2. And if we put in a 2, it means we also need to cancel that 2 out by putting in a
1/2.
1/2. Good. So now we're looking at 1/2 the integral secant squared u du. Right, our 2 dx becomes du. And so we just integrate that, which should be 1/2. What's the integral of secant squared u?
Tangent u.
Tangent u, and plus our constant. And now we just go back and replace the u. 1/2 tangent 2x plus our constant. Good or no?
Good.
All right. Any questions? All right, let's do this one. Any thoughts? All right, so for the previous one, we had to rewrite the trig and we had to do a u sub, right? So this one, cotangent squared, is there a formula that we have to integrate cotangent squared?
No.
No, so we're probably gonna have to rewrite the trig. And my guess is we're probably gonna have to do a u substitution also for the 3x. Would you guys agree with both of those?
Yeah.
Yeah.
All right. Well, let's do the u sub since we know we got to do that. U equals 3x du is 3 dx, which means we'll put a 1/3. We'll put a 3. And we can then make this 1/3 the integral of cotangent squared u du. Everybody good with that? Oops. Yeah, I said cotangent squared. Now what?
We rewrite it as like cosine squared u over sine squared u.
All right, so that's one option that we might think about, cosine squared u over sine squared u. And what would you do from there? This one becomes a bit of an issue.
Would you do another u sub?
Sorry, say that again?
Would you do like another u sub?
Yeah, so that would be the thing we would try. Now, we need to get rid of the stuff that's in the denominator. So we'd either have to let u equal sine or let u equal sine squared. But that becomes a problem because if u is sine, du is cosine. And I have a cosine, but then I have an extra cosine left over. And if I let u be sine squared, then du would be 2 sine u cosine u. And I've got the cosine u, but I then would have an extra cosine u, and I'd be missing a 2 sine u. So rewriting it in this way, actually in this case, isn't going to help us out because neither of those U substitutions work out very nicely. We got to think of another way to rewrite this. We've got to close our eyes and go back in time to the days of the ancient Greeks and think about the ancient Greeks to rewrite this. So everybody do that. Go back in time to the days of the ancient Greeks. And who will tell us how to rewrite this? Who's your favorite ancient Greek mathematician?
Pythagoras.
That's right, he is. Yes, Pythagoras is your favorite ancient Greek mathematician. And I recall there being some things called the Pythagorean trig identities that you all memorized and knew from last year. Right? One of them was sine squared plus cosine squared equals 1. Remember that one?
Yes.
No, good. And another one was, because that one, sine squared plus cosine squared equals 1 doesn't really apply to cotangent. And then we had another one that was 1 plus tangent squared equals secant squared, which also doesn't really apply because this doesn't have a tangent or a secant. And then there was another one that included a cotangent, and it was one
Plus cotangent squared x equals cosecant squared x.
Yeah. That one seems like a good one to use, right? So we'll have 1/3 the integral of, instead of cotangent squared, we'll write cosecant squared u minus 1 du. Good? Everybody good with that?
Good.
And now we'll integrate. We have a rule for cosecant squared. What's the rule for cosecant squared?
Would it be
It's negative cotangent u.
Mm-hmm. And then the integral of minus 1 should be minus
X.
well, in this case, what's our variable?
U.
Yeah, so it's got to be minus u. So be careful with that. Don't just make the minus 1 an x, right? Make sure you make it the right variable, especially if you've done a u substitution already. Because if you just make that an x, and then you wouldn't be subbing the 3x back in, so you're going to end up with the wrong answer. And then plus our constant. So we end up with negative 1/3. What happened there? Negative 1/3 cotangent 3x, and then minus 1/3 of u, which would just be minus x, and then plus our constant. Good or no? Any questions, any issues with that? Everybody okay there?
Yes.
All right. Let's take a look then at another one. Cosine cubed x dx. Any thoughts there on that one? First thing we want to look at anytime we're doing an integral is there just a rule for cosine cubed on our integral formula sheet?
No.
No, there's not, okay? So no just rule for cosine cubed, which means we're going to have to do some sort of rewriting or u substitution or both. Any thoughts on what to do with it then?
Could we just break it down into cosine squared times cosine of x?
Sure. cosine squared x times cosine of x dx. All right, that's great. Now, that's the right start, but it's not off the bat really super helpful because we can't just integrate cosine squared times cosine because there's a multiplication between them. And we need to be able to still substitute something out and probably still rewrite something as well. So what's the next step going to be? Yes, that's right. It's taking another step back in time to the ancient Greeks. Good. I knew somebody was going to say that. And what will we do as we step back in time to the ancient Greeks?
Rewrite cosine squared x as 1 minus sine squared x.
Great. Thank you. Good old Pythagoras. Such a helpful guy. Now we got 1 minus sine squared x times cosine x dx. All right, let's look for a u sub. I think that's enough rewriting. Anybody see a good u sub they want to use? No? Anybody want to guess a u sub to try?
Sine of x.
All right. U equals sine of x. That sounds like a good one, actually. Usually people go with like, let's try cosine. And then they go with, let's try sine squared or 1 minus sine squared. But sine is going to be much better. If we let u equal sine x, what's du equal?
Cosine.
Cosine x dx. And so what we want from our u substitution is something fairly simple that when I take its derivative, gives me another piece of it, which it does. It gives me another piece of what I'm trying to integrate. Right? And it turns everything else into terms of u that can easily be integrated. So this just becomes an integral of 1 minus u squared times du. Everybody good there? And what should that become? What's the integral of 1 du?
U.
And the integral of minus u squared?
U cubed over 3.
Plus our constant, and then we just resubstitute back in. All of our u's will become sine x's. So we've got sine x minus sine cubed x over 3 plus our constant. Hold on 1 second, everybody. Sorry about that. Everybody good with that being the answer? Any questions on that? All right, I'll assume everyone's good. All right, let's look at this one. So first off, this one's a little different because it's no longer an indefinite integral, right? It's a definite integral, 0 to pi over 3 of tangent x secant squared x dx. And so we'll have to worry about how to use the, how to deal with those limits in a bit. But what do you think we should do to try to integrate this to begin with? First off, look, is there any rule specifically for tangent x secant squared x?
No.
Okay. And then if we see a u substitution that'll work nicely, we should, and if not, we should try to rewrite the trig. So does anybody see a u substitution that they think will work out nicely?
Tangent x.
All right. Tangent x seems like a good choice, right? Because if u is tangent x, what's du?
Secant squared x dx.
Exactly. And so the whole secant squared x dx will disappear and become du. And we'll just end up with an integral of u du. Everybody agree with that? Everybody good with that? Okay. Now, what is this 0 and this pi over 3? What variable are those numbers representing? Or what variable represents those numbers?
X.
X does, right? But we've gone from an integral that was all in terms of x to an integral that was all in terms of u. So in order to evaluate this, we need to change each of these limits from an x value to a u value. So what is the tangent of 0? Right? What is u if x is 0? The tangent of 0, which is
0.
yeah, tangent of 0 is 0. So that one happens to stay the same. What about if x is pi over 3? What's the tangent of pi over 3?
√3.
Yeah, okay. So now we will have an integral from 0 to √3 of u du. And when we integrate, it becomes u squared over 2 from 0 to √3, which should be what? 3/2 minus 0, or just 3/2. Everybody good there? All right, you're all excited because we only have 4 pages left, right? Page 14 out of 18. We got 15 to 18 to go. Well, we're going to spend a little extra time talking about this problem. Anybody see a different u substitution that we want to try to use for this one? This is a good answer. I got no problem with this answer. It's a correct answer. But it's not the only way we could have done this. What else could we have used as our u sub?
We use cosine x.
Could use what? Sorry.
Cosine x by like rewriting tangent.
Okay. That's going to be possible. True, right? We could. Let me rewrite this as an integral from 0 to pi over 3. If we rewrite it as sine x over cosine cubed x dx, right? We could let u equal cosine x, and then du would be negative sine x dx. Everybody agree with that? Put some negatives in there, and we end up with the opposite of the integral of what? Negative sine x dx is our du over u cubed. And we still got to change these from x's, x equals 0 and x equals pi over 3 to u. So what's the cosine of 0?
1.
1. And what's the cosine of pi over 3?
√3/2.
Nope. cosine of pi over 3 is
1/2.
1/2. And we had a rule for integrals that said if I wanted to flip the limits of integration, which would be nice because then I'd have my smaller number on the bottom and my larger number on the top, I could just flip the sign. Remember that rule from a while ago? This would give us u to the -3 du to integrate. And if we integrate u to the -3, what do we get? U to the -2 divided by -2, evaluated from 1/2 to 1. And let's see, u to the -2, which would be -1/2u squared, right? If we wanted to rewrite that. And what would that give us? Should give us what? -1/2, right? Minus -1/2 times 1/2 squared, which would be 1/4. And what would that give us? -1/2 plus 2, which would be 3/2, right? 2 times 1/4 is 1/2, and 1 divided by 1/2 is 2. So it looks like we get the exact same answer, wouldn't we?
Yes.
Yeah, that's kind of cool, huh? Okay. All right, moving on to the next one. Now, let's see if we can find another way to do this. Anybody see another substitution that would work out nicely? Without rewriting any of this in any way, without rewriting any of the trig?
Secant x.
All right, secant x seems like a reasonable option. The du would then be the derivative of secant, which is secant x tangent x dx. And if I think about this, if I get rid of one of the secant x's as a u, I'm left with a secant x tangent x dx, which would be my du. So we'd end up with u du. And instead of 0 to pi over 3, we'd have to find the secant of 0, which we know the cosine of 0 is 1, so the reciprocal of that's just 1. And then we'd have to find the secant of pi over 3. What would the secant of pi over 3 be?
2.
Should be 2. Good. So we have 1 to 2, which gives us u squared over 2 from 1 to 2, which should be what? Should be 2. Right? 2 squared is 4 over 2 is 2, minus 1 squared over 2, which is 1/2, which gives us 3/2. Still comes out to be 3/2. Good? Everybody good with that? Is that enough ways to do that one or no? Should we do one more?
I think that's good.
That's good. Okay. All right. We also could have done a substitution where u is equal to secant squared, and we'll work that too. Now, we'll note that in each of these cases, we got a different integral, and we did a different u sub, but we always got the same answer, right? What if I had taken this, and sorry, we're not going to be done with this problem, only sort of. What if I took off the limits of integration and just did it like this? And let's just look at 2 of the different ways here. Let's look at when we did u equals tangent x, and let's look at when we did u equals secant x. And so this way du is secant squared x dx, and this way du is secant x tangent x dx, right? And in both cases, what would we get? We'd get an integral of, if u is tangent and du is secant squared, we just get u du. And on this side, we just get, again, u du, wouldn't we? Everybody agree with that? Do y'all agree that that's the same on both sides?
Yeah.
Except the problem is, when I substitute my u back in, this side gives me tangent squared x over 2 plus a constant. And this side gives me secant squared x over 2 plus a constant. Now they're both being divided by 2, and they're both having a constant added to them. But tangent squared is not the same thing as secant squared, is it? So which of these answers is correct? Or are they both correct? Or are neither of them correct? Cool. No
They're both
response.
correct, right?
They're both correct. Yeah, they're both correct, but how can they both be correct? What's the difference between them? The value of the constant is different for each one. Let's take a look. We had tangent squared x over 2 plus a constant. We'll call it constant 1. And on this side, we had, it's not tangent, it's secant squared x over 2 plus some other constant, perhaps. And we're claiming that these are equal to each other. So let's leave this side as is. But rewrite this secant in terms of tangent. How do I write secant squared in terms of tangent?
1 plus tangent squared.
1 plus tangent squared x, right? Yep, over 2 plus this second constant. And so over here we have tangent squared x over 2 plus some constant. And on this side we have a half plus tangent squared x over 2 plus some other constant. And hopefully we should see that those cancel out, right? And that the constant that's attached to the tangent squared x over 2 has to equal 1/2 more than the constant that's attached to the secant squared x. So the results that we got were not equivalent, even though they're both correct. They just differ by constant. And this is a really important thing that happens with integrals sometimes, is that you might get, for indefinite integrals, you might get two different answers, or two answers that look very different from each other, and that are not equal to each other, but they differ by a constant, and that's okay. And because all that integration is doing is it's finding us some function that we can evaluate to find the area underneath the curve. And both of these functions, tangent squared x over 2 and secant squared x over 2, right? They both worked to get us 3/2, didn't they? Okay. Because that constant doesn't matter when you do a definite integral, but when you do an indefinite integral and you have to include that constant, you might get different looking answers. Does that make sense or no?
Yeah, that makes sense.
Cool. So just something, I think it's important that you guys see, because especially as you move up to higher calc classes, higher math classes, and do some, all the integrals we're doing right now are pretty simple integrals in the great scheme of things. You're going to see some really complicated integrals where there might be 4 or 5 different methods to go about it, solving them. And, you might get an answer that looks very different than what somebody else in your class might get, or what I might get as, put on the answer key or something. But that doesn't mean that your answer is necessarily wrong. There just may be a way to equate them with a different constant. let's do another definite integral with a u sub. So anybody have any thoughts on what we could use as our u sub for this one?
Could we do x squared?
All right, we could do u equals x squared. Generally, though, if we have a denominator to it and it's got a constant attached to it, we usually want to use that constant as part of it, because if I put the -4 there, it doesn't affect the derivative, right? du will still be 2x dx. But now instead of having u -4 down there, I'll just have a u down there, which will be easier to deal with usually. Does that make sense?
Yeah, that makes a lot of sense. Okay.
Yeah, so the -4, you can leave the -4 off if you want and just do x squared, but then you end up with having to do a second substitution to get rid of that -4 later on. So it's better to just do it at the beginning. So if I need to have a du of 2x dx, what do I need to multiply my numerator by?
Two.
2.
Yep. And if I multiply my numerator by 2, what do I need to do outside my integral sign?
Multiply by 1/2.
Multiply it by 1/2. Good. So we've got 1/2 of an integral of du over u from 0 to 1. That was with a question mark at the end, from 0 to 1.
No.
No, because we have to turn those zeros and those ones into terms of u. So 0 squared minus 4 is -4, our new lower limit. And our new upper limit ought to be 1 squared minus 4, or -3. Everybody good with that? And hopefully you've gone through over the weekend like I asked you to and memorized all of the integrals on that sheet. What's the integral of du over u?
Natural log absolute value of u.
Natural log absolute value of u plus our constant. And so now we'll just evaluate. Oh, sorry, this is a definite integral, not plus a constant. And we'll just evaluate from -4 to -3, which ought to give us 1/2 natural log of 3 minus natural log of 4, which is a good answer. And you should be aware that you might not see that answer. You might see an answer like 1/2 natural log of 3/4 on a multiple choice test also. Right, just using log rules to combine ln3 minus ln4. I would take this answer, but if that wasn't there in the multiple choice, maybe this would be. Or you could pull that 1/2 in as a square root, as a power of 1/2 on the 3/4. This would be a good answer. And also maybe you might see that in the multiple choice. Or you might see something like natural log of √3/2, where they actually take the square root. That'd be a good answer too. Or you might see something like natural log of √3 minus natural log of 2 in the multiple choice. I mean, I would take any of those 5 answers. Any of those 5 answers is good with me. But just be able to convert back and forth between any of them in case it was a multiple choice question. Any questions there? All right, we're going to do a couple more just regular u substitutions here. I think I got all indefinite integrals the rest of the way, but just remember when you do the definite integrals, all you really have to do is change those limits of integration. And you'll note that for the u substitutions that were definite integrals like this one, right? Once we got natural log of u, once we took our integral in terms of u, since I'd converted these x values into u values, I don't have to convert this back into x. I can just evaluate it as is. Everybody's noted that we didn't convert back to x because we're going to get a numeric answer.
If we did like convert it back to x and then like evaluate it at the original interval, would it give the same answer?
You would get the exact same answer, but yeah, just make sure if you do that, you go back to 0 and 1. But I mean, really, that's just making you do extra work that you don't need to do. I wouldn't recommend doing that, but it's okay if you want to.
Okay, thank you.
All right. So we got 4x over root x squared plus 9 dx. Any suggestions for the u sub here?
X squared plus 9.
That seems like a reasonable place to start. U equals x squared plus 9. Get rid of most of the junk that's in the denominator. What's du going to be?
2x dx.
2x dx. Good. Which means, well, I've already got a 2x up there. In fact, I have an additional 2 up there, don't I? So the extra 2, maybe we pull out outside the integral. And then we have 2x dx over root x squared plus 9, which then becomes what? 2 times the integral. And this x squared plus 9 will become a u. And so a square root of u in the denominator. What's the square root of u in a denominator? That should be u to the negative 1/2, right? And our 2x dx is du. And when we integrate u to the negative 1/2, what do we get? Should be 2u to the positive 1/2 plus our constant. And so we end up with 4 square root of u plus c. Good or no?
Good.
All right. 2 more to go. Integral of x cubed root x squared minus 1 dx. Anybody got a good u substitution there?
X squared minus 1.
All right. And du is 2x dx. So I'm definitely going to need to put a 2 in, right? Which means I'm going to need to put a 1/2 outside. And x cubed I could break down into x, right, to give me the 2x dx, and then an additional x squared. And I might as well, I'll just rewrite that for now. Okay. Root u dx. And what about my 2x dx? That's just my du. So I'm almost there. And now I've got 1/2 of the integral of x squared root u du. And I can't integrate it because of the x squared. So how can I deal with that x squared?
Solve for x squared in terms of u. So x squared would equal u plus 1.
Exactly. I've got an x squared up here. X squared is equal to u plus 1. So now I can resubstitute that x squared into u plus 1 out. So 1/2 the integral of u plus 1. And root u is u to the 1/2, right? And then what? How do I integrate this? That's like some of the simple ones we were doing at the beginning. What'd you say?
You just have to use the distributive property and just multiply it out.
Yep. U times u to the 1/2 is u to the 3/2. And 1 times u to the 1/2 is u to the 1/2. And then you just integrate. So we got 1/2. The integral of u to the 3/2 ought to be 2/5 u to the 5/2. And the integral of u to the 1/2 ought to be 2/3 u to the 3/2. And now, since this is an indefinite integral, we got to go back to terms of x, and I'll distribute the 1/2 through. So we got 1/5 x squared minus 1 to the 5/2 plus 1/3 x squared minus 1 to the 3/2 plus a constant. Any questions on that one? All right. Last one for today. What's our u sub going to be?
X squared minus 1.
All right. Same as before, u is x squared minus 1. Du is still 2x dx. We'll still need a 1/2 and then a 2 there. And we're left with an x to the 4th if we pull the x out of the x to the 5th. And the 2x dx should become our root u, and our x to the 4th. Just because we don't have an x to the 4th up here anywhere doesn't mean that we can't turn x squared, which is u plus 1, into x to the 4th, right? X to the 4th ought to be x squared squared. So this is 1/2 the integral of x squared, which is u plus 1, squared, times u to the 1/2 du. Everybody good there? So the important thing is if you're left with some x's, always try to look back up here. And if there's a way to take your original u substitution and to turn it into whatever that x value that you have left is, great, do it. And then you should be able to integrate. If you end up with some x's over here still, and you can't rework this to figure out what it is, chances are you picked the wrong u sub and you got to find something else. So how am I going to deal with u plus 1 squared times u to the 1/2?
Just expand out the u plus 1 squared and then multiply by u to the 1/2.
Perfect. So u plus 1 squared, first term of that's going to be u squared, right? And then times u to the 1/2 ought to be u to the 5/2. Second term will be a 2u. And when you multiply 2u to the first by u to the 1/2, that'll give you 2u to the 3/2. And then the last term will be a plus 1, which will make it a plus u to the 1/2 du. So everybody good with expanding all that out there? Okay, so now we've still got the 1/2. We'll integrate each of those three terms. And after we integrate those three terms, we'll turn it back into terms of x and be done with it. So u to the 5/2 becomes 2/7 u to the 7/2. And then this will go up to 5/2. And then we'll multiply by 2/5. So that'll become 4/5 u to the 5/2. And then the last one will become plus 2/3 u to the 3/2 plus our constant. Everybody good with that or no? All right. 1/2 of 2/7 is 1/7. So we have 1/7 x squared minus 1 to the 7/2. And then 1/2 of 4/5 is 2/5 x squared minus 1 to the 5/2. And 1/3 x squared minus 1 to the 3/2 plus our constant. And that's it. Any questions on that or anything else? That should help you to get through everything that's left on that integral homework assignment that's due tonight.